Hey y'all, welcome back to another video, and today's video we are going to be analyzing exponential growth and tetrated growth. Now this is going to be very because now we're going to test some values to analyze their growth. In the first column we have x squared, second we have 2 to the x, third we have x to the x, and the fourth we have x tetration x. And note that this we can also write this as x double arrow x. This is also another notation to write x tetration x. Okay, so yeah, basically, yeah, that's simple. We can also write we can write x squared as x to the arrow of 2. This just means exponential growth, 1 arrow. But we don't. But usually we write like this. Okay. So yeah, and after tetration there's something called pentation. But pentation is very large. Pentation looks like something like this. Now pentation is like this. Basically you have x and then 1x down. This is equal to x pentation. This is repeated tetration. And tetration is repeated exponentiation. So this would just be like x tetration x, like x times. This is huge. See? So that's why I'm not sure, we're not going to do pentation. We're going to focus on the tetration for now, okay? So as you can see, this is a power polynomial. These are all exponentials. This is repeated exponential polynomial. But I don't know. I'm not sure if it's a polynomial because let's call this an expression, okay? Okay, this is an expression basically. So for the first polynomial we have x squared. So we're gonna test values from 0 to 5 to see their growth. Now for 0 we get 0 squared, and the square of 0 is just 0. So let's write down 0 right here. Okay. Alright, and for the next one, I'm gonna use a red pen. So for the first one, we have 0, okay? Because the square of 0 is 0. Alright? Now for the next one, this one like this. 1 squared is 1, okay? 2 squared is 4. 3 squared is 9. 4 squared is 16. And 5 squared is 25. So we could go from 6, but we could do 6, but we're gonna do only these values to see. Okay? Now strong line. Okay, so for 0 and 2 to 0, 2 to 0 is actually 1. And then 2 to the 1 is 2. Okay, now 2 to the 2 is 4. 2 to the 3 is 8. Okay, and 2 to the 4 is 16, and 2 to the 5 is 32. Okay, so let's analyze our growths from here. Okay, 0, 1. So this is 1 bigger, this is 1 bigger. These are equal. This is a coincidence. This is 1 bigger, equal, and this is no, actually in this case, this is 1 greater than 2 to the x. This is 1 less. So, but the thing is, the growth is a little more faster here because from 16 we go from 32. This means we're adding like 16. But in this case, we're only adding 9. Yeah, plus 9. Okay, this is a growth. We only have this much of a growth. And for suddenly from 0 to 1. Okay, same growth. The growth is equal at 0 and 1 because we're adding 1 here. And we're also adding 1 here. okay? But from 0, see, this is a +3, but this is only a +2. Interesting. From 4 to 9, we have a +5. From 4 to 8, we have a +4. Interesting. So it looks like this growth is equal. This is bigger than that. This is bigger than that, the growth. And the growth, you know, at the end, if you keep choosing bigger values, this would eventually become more bigger than this. So I'm just gonna say this, that basically x squared is less than 2 to the x for all x. Now, but in this case, we're only considering positive integers. Yeah, okay, so in terms of positive integers, this will be greater than this. Eventually, it will, because at first it looks like, oh, this is getting the finish line, but when you take 2 to the 6th power, the 6 squared is 36. Let's do it here. Look, 6 squared is 36, but 2 to the 6th power is some big number. We can break it down like 2 to the 3 into 2 to the 3. Okay, because if you just add exponents to get back to this, so we can write this as 8 into 8, because 2 cubed is 8, and we'll get 64. And we can see that 2 to the 6 is greater than 6 squared. So eventually, it would be the winner. The winner would be 2 to the x, because at first it looks like it's going slow, but you know, eventually it kind of crosses the finish line. Okay, so yeah. Okay, so now we've done this. Now we're gonna go to a much higher one, x to the x. Okay, but this is gonna be a rapid growth. So look, but this is a weird thing. We have 0 to the 0th power for x equals 0. Now in this case, this is not defined. Okay, because 0 to the power of 0 is undefined. Because we can write, suppose I write, if I write 0 to the 0, I have 0 to the 2 minus 2. I can write 0 to the 2 minus 2 as 0 to the second upon 0 to the second. Okay, because using the last exponent, if the powers are subtracted, we can write them as a quotient. And if we simplify this, we get 0 divided by 0, which is undefined. So this is why 0 to the power 0 is undefined. So interestingly, for the first case, this is undefined. Okay. So at x, we can't say whether which one is higher at x equals 0, because this is undefined. Okay, now for at x equals 1 we get 1. At x equals 2 we get 4. Okay. At 3 we get 27. Whoa, look at this. We go from, if we use positive integers, okay, we're adding 3. Okay, we're adding 3. And this is a rapid growth. Yeah, we're adding 13. Pretty cool, right? And see, 4 to the 4th, let's find, see 4 to the 4th, we can write this as 2 squared to the power 4. 2 to 4, yes, 8. So 2 to the power 8. And we can write 2 to the power 8 as 2 to the power 4 into 2 to the power 4. We can break it down. And this will just be 2 to 2, 4, 1 to 8. So 16. Wait, 2 to 4, 4 into 2 is 8. 8 into 16 into 16. Now this is the square of 16. This will just be 256. Okay? So we get that this, for 4 to the power 4, this will just be 256. Whoa! This is a massive growth. Now the reason why the growth is so massive here is because, see, in this case, the base is increasing only, and in the second case, the power is only increasing. But in the third case, both the exponent and base are increasing by 1. Now this is why the growth is so rapid, okay? So this was happening. And, oh my god, 5 to the power 5. And luckily we can, even though it's a big number, we can find this. 5 to the power 5. Let's write this as 5 to the power 5. We can write this as 5 squared into 5 cubed. Okay, so this will be 25 into 5 to 5, 25 to 125. We can write this as 5 squared into 5 squared into 5. Yeah, because 2 plus 2 is 4, 4 plus 1 is 5. We're breaking down the exponent. So we will get 25 into 25 into 5. So 25 to 25 is 625, and 625 into 5 is 3125. If we do the math, so we will just get 3125. Whoa! Look how big. At first it was slow, but now it's big. From here, now from 27, the difference between 256 and 27 is vast. It's bigger than you could ever imagine. So I guess we can say that x to the x is greater than these both in terms of positive integers. It makes sense though, because in exponential growth, it would make sense because if both the base and exponent are increasing at the same time, obviously we would get a much bigger result. And the difference between this and that, wait, okay, 246, 236. So plus 229. 229. Wow, we're adding 229. That's a big. And from here, okay, this is just a big gap. We're going directly from the hundreds to thousands, 3,000. From the tens place numbers to the hundreds, then from the hundreds to the thousands, like bam, and just one step. You're just growing, and this would just be, I don't know, that's something like, this would be a big number we're adding, okay, here. Probably, I don't want to do the math, but the difference between this would be like big, telling you, bro. And I just typed 100. Okay, yeah, so basically we would be adding something like that. Let's approximate, because I don't want to do the math now. Okay, so that's 3,000. Difference between 3,000 and 250. That'd be pretty big actually. So yeah, wait, subtract 100, 2928. Okay, so 279. The around 275 is where we would be adding. So this would be like a big growth between this and that. Okay, guys, if you do the math, the difference between these two would be 2869. So you can see how big the growth is getting. And for titration, it's going to be pretty messy. Telling you. But you see, the growth is like, there's a big growth. That's the conclusion. And this is what's happening. See what actually, now if we analyze something in x squared, 1, we're adding 2, and here we're adding 2, okay? But from 5 to 9, well, yeah. And we're adding 5. From 9 to 16, we're adding 2 more to 2. So it'll be 9. So that's what we're adding 4. From 9, we're adding 9. To, get it? This is pattern. We're just increasing by 2. But we're increasing 2 from the before term. Like 1, 0, 1, 1, okay, 1, 3. Now 4 plus 2 is 6. We're adding another 2. Yeah, that's what's happening here. Like, okay, wait, nah. Alright? So basically, in conclusion, what's happening is the growth is getting big. Very big. And if you come over to here, x titration x basically means x to the power x times. But this is big. Now suppose we have 0 tetration. This will be undefined because we're raising 0 to the power 0 times. So like 0. I think this is undefined. Undefined. Because 0 to the tetration 0 is equal to the. It's just undefined because 0 to the tetration 0 is raising 0 to the power, like raising 0 to the power of 0 times. Like, and 0 to the power of 0 is undefined as well. It's undefined, okay? But this will be rapid growth. At 1, okay, this is equal because raising 1 to any power is 1. From 2 tetration 2, but there's a coincidence. The 2 tetration 2 is equal to 2 squared, which is equal to 4. Now that's a pretty coincidence. So because see, 2 into 2 is 4, 2 plus 2 is 4, because there's a pattern between I and 2. And just doing it 2 times. So this is also 4, okay? This is also equal. And for 3, okay, this is where the magic starts. At 3. Now 3, make it 3 tetration 3. Which would just mean 3 to the power 3 to the power 3. Whoa! Oh my god. Now this is just a big number. So look, at most, we could certainly say that this number, which would just be 3 to the power 27, if we simplify this, so I guess we could say this is 3 to the power 27. Now we can conclude that this is bigger than all of this. All of this. It's way big. And if you go to 4, which I don't want to do, because it's going to be frightening. Frightening. Literally. So, but you know what, let's just do it. Who cares? We're going to do it. Okay? Now 4 tetration 4. So using definition, we're raising 4 to the power 4 times. So like, see, So like it'll be something like this: 4 to the power 4 to the power 4 to the power 4. Oh my god! This is humongous. This is humongous. I think we can conclude that this number. So I'm not even gonna simplify any of this. I'm just gonna write. This is just. And look, 4. This is also a repeat exponential. 4 to the power 4 to the power 4. Which is just 4 tetration 3. We can write that as like 4, 3. 4 tetrated 3, but we can write this as 4 tetrated 3 also. Oh my god. Now we can say that this is a big number. This number, it's big. Just admit it. It's big. It's a big ass number. We don't even have to do any calculation. Just by seeing this number alone, will make your brain explode. Of this number right here. Yes, we can conclude that this is bigger than all this. Now for 5, oh god. Yeah, 5 to traded 5 will just be 5 to the power of 5 to traded 4. There's a reason we're doing this, is because 5 to traded 4. So this would just be 5 to the power of 5 tetrated by 4. Tetration. We're using tetration here. Now, what's happening here? I should probably make some space. Do it here. Okay, yeah, so 4 to the power of 4 tetrated 3. And here, it would be 5 to the power of 5 tetrated 4. Because this will just be 5 to the 5, 1, 2, 3, 4, 5. And there's a pattern here. We can also, this is also tetration. So there's a pattern that when we're, basically, when we have a tetration, tetration x, we can write this as x to the power x to the power x. And this, we also have a repeated tetration here. X to the power x to the power x. So you can also write this as, as x to the tetration of x to the tetration of x minus 1. That's what we're using here basically. So this will just be something like like x tetrated x tetrated to x would be x tetrated of x to the power x minus 1. Tetration, okay? Now this is repeated. Yeah, x to the power of n minus 1. No, x minus 1. Okay? That's what you're using here. For 5, it would be 5. For x equals 5, it would be 5 raised to the power of 5 tetrated 4. Because there's a power tower. Like x to the x to the x to the x. There's a repeated exponential here also. So that's what's happening. And same for pentation. Where it is too big, we all know that. So we can conclude something here actually. That as we go up from exponential to tetration to pentation and so on, the values will be greater and greater and greater and greater and greater. Like immensely greater. So we can conclude that we can make a pattern here. There's a conclusion here. The conclusion is that this is less than, so yeah, this is less than this. Or can be equal. Because in some cases this is equal. And this is 2 to the x. Yeah, this is less than, but also it can be equal to, because 2 to the x, it was here. And xx, this was also equal. It could be equal also in some cases, as we observed. And x squared, it could be equal also. So this is less than or equal to. Now we have a pattern here. The reason we have less than or equal to is because there's a pattern. That's how that works. This is our conclusion we have. Okay? So now that we've observed all this growth, we made a conclusion. So now, I think we can learn how to graph. Now, if you want to know, we'll do some basic of graphings. But graphing power functions and exponential functions. Now,